Welcome back. In the previous lecture, we discussed the kind of experiments that Madame and Pierre Curie did, for which they were later awarded Nobel Prize. In the next few lectures or the next few weeks, we will look at various aspects of nuclear science and engineering. It's good to have a big picture on where we are heading towards. So I felt one way we can do this is to go over the various Nobel Prizes that have been given in nuclear physics and chemistry so that you get an understanding of when this field was most active and what is the emphasis in different decades. X-rays has nothing to do with nuclear physics per se, in the sense that it is more to do with rearrangement of atoms, right? The way X-rays are generated is when a metal surface is exposed to high energy electrons. These high energy electrons excite some other electrons, and when there is a de-excitation, X-rays are ejected, right? That is not really something to do with nuclear physics, but it had um, consequences for nuclear physics. So the study of X-rays led to Ron Becquerel's work and so on, which is where nuclear physics originated. So, so if you look at the Nobel Prizes, they are close to each other, suggesting that uh, these were sort of close related to the work of Becquerel, um, which was followed up by Madame and Pierre Curie. So they discovered radioactivity, especially of uranium, and the Curie, Madame Curie did many other work later, for which she got one Nobel Prize was in physics and the other was in um, chemistry. So Leonard, we have talked about the Leonard tube. This is to do with the penetration depth of cathode rays. So for which he got the Nobel Prize in 1905. This is important because uh, even though again it is nothing to do with nuclear physics per se, but this aspect of different radiations, different emanations having different penetration depth is an important aspect to understand the nature of emanations. And Leonard's tube particularly helped in understanding these features. Then Chadwick got the Nobel Prize for neutron in 1935. So when all these things were done, actually the concept of neutron was not even there. So why neutron was important? Because it was a heavy particle and it was neutral. It was not charged particle. Before that, only these rays, um, photons, were the emanations that were not deflected by magnetic field. So this was the first heavy particle that was not deflected by magnetic field. So suggesting that nucleus, in addition to having something like a proton, okay, so that uh, a positive charge, it also has a neutral particle. So Anderson got the Nobel Prize in 1936 for positron, right? So this is like an electron. The mass of positron is like that of an electron, but it has a positive charge. So also notice the gap. So there are three closely spaced Nobel Prizes. Then after 30 years, there was a Nobel Prize, and there are again a bunch of Nobel Prizes that came together. So once you have a neutral particle, the neutral particle has an advantage that if you have a high energy neutron, they can smash into a nucleus, which can give rise to transmutation. Um, if you have a charged particle, let's say a proton, which is heavy but positively charged, so there is repulsive interaction between a proton and neutron. So the access of high energy proton to a nucleus is less compared to high energy neutron. Uh, so that gave rise to a lot of transmutation. Fermi, who did lot many things in all aspects of physics, he's sort of called the last complete physicist in the sense that he had a great breadth and depth in understanding. Excuse me. He was given the Nobel Prize for transmutation via neutrons. Fermi not only worked on many aspects of physics, he did very creative experiments and also devised the theory for that and contributed to um, nuclear energy per se, what's called the Fermi pile, which led to uh, suggestions on atomic bomb and so on. So uh, then Rabi got the Nobel Prize in 1944 for magnetic properties of nucleus. Then there's a Nobel Prize for cloud chamber. This, again, it's a way of visualizing many aspects of uh, uh, nuclear emanations, trajectories of particles, and so on. So that was in 1948. And amongst the forces, there is the gravity, electrodynamical forces, uh, the weak force, the force wherein most experiments have been done is on nuclear forces. It is still many an unknown, and many aspects of nuclear forces are still not well understood, because what are the forces that holds all the positive charges, the protons together in a very, very confined region of nucleus, is um, a great mystery. Yukawa um, contributed to this and contributed to what are called particles called mesons. Okay, so then again, another Nobel Prize was given for visualization techniques in nuclear physics, and Powell also worked on mesons. So this was an important Nobel Prize for artificial transportation. For a long time, um, the radioactivity that was studied was in elements that had a natural tendency to radioactively decay. So this Nobel Prize was an artificial um, transportation. And if you've seen uh, this very fascinating series called Chernobyl, available, it was a six-part series on Chernobyl accidents, and perhaps you may have observed there is this bluish kind of glow that comes. Okay, in many nuclear reactors, you would see this bluish kind of glow. Um, uh, there is a water photon travels at a lesser velocity, and certain nuclear emanations travel faster than um, protons in water, and in such interactions give rise to certain radiation. These are called Cherenkov radiation, and Frank and Tam, they did the theory for these radiations. All of them got a Nobel Prize for explaining and observing these radiations. Then there's a Nobel Prize for um, antiproton. Sergei uh, was a collaborator of Fermi. He did a lot of interesting work, and he wrote I think, one of the first uh, book. I think it was called Nuclear and Particle Physics, connecting both. So, and then there's another visualization technique on bubble chamber that was a Nobel Prize in 1960. Then there's an important effect which connects certain aspects of the nucleus and with scattering of electrons by the nucleus. So it's a very widely used spectroscopic tool called Mossbauer spectroscopy. And Hofstadter, I think, did the theory for Mossbauer spectroscopy. So that Mossbauer effect. So that was in 1961. Uh, One of the great theorists is Wigner. He talked about symmetry principles and built a model for a nucleus. So this Nobel Prize was for theoretical efforts to understand nuclear structure. So that was in 1961. Wigner went on to do a lot of interesting work using group theory. So his book, which is fairly mathematically involved, is about how to utilize group theory to understand variety of symmetry principles in nature. But his original work was on nuclear physics, was in nuclear physics, and similar methods can be used for understanding electronic structure. In fact, in 60s and so on, many people who went on to do great work in quantum chemistry, understanding the electronic structure, came from nuclear physics. So the mathematical tools and which were originally developed in nuclear physics was utilized in quantum chemistry later. Bethe, Hans Bethe was an important nuclear physicist who did a lot of work, not only in nuclear physics, but also in electronic structure and so on. So he um, rationalize how stars generate energy and proposed models. He was one of the greatest theoretical physicists of the modern times. For his work on nuclear reactions in stars, sun, and so on, he got a Nobel Prize. Then other important aspects of a nucleus, there are collective motions within the nucleus. Nucleus has a lot of substructure. There are excited states for nucleus. See, this high school representation of nucleus being a spherical object is an approximation. It's a very good approximation, especially when it is in the ground state. But there are many excited states possible for nucleus, wherein nucleus is not at all spherical. For elaborating and explaining collective motions in nucleus, um, the son of Bohr. Okay, so this is not Niels Bohr, the son of Bohr. He and two others got the Nobel Prize, and in 1983, perhaps the last Nobel Prize in nuclear physics. It was on nucleosynthesis. We'll try to elaborate on this at a later stage. What does it suggest? It's been 40 years since the last Nobel Prize. In a way, the entire community has moved away from nuclear physics to particle physics. Nucleus is a fairly complicated object in the sense that there are many body interactions, the forces are not that well understood. So, physics is uh, typically understood in a simpler system. So, many of the people who worked in nuclear physics have moved on either to particle physics or other fields. So, it's been 40 years since the last Nobel Prize in nuclear physics was awarded. So that suggests that new kinds of experiments have or can be done to unravel mysteries of nucleus. So these are all Nobel Prizes in nuclear physics. There have been um, Nobel Prizes in chemistry connected with nuclear chemistry. So Rutherford, uh, in a way, uh, sort of suggested something important, right? There was this hypothesis, I think, by Dalton, I think, so that the or it even existed from early Greeks and even in early literature uh, so from Vedic times, that there is an elemental particle which cannot be broken down, right? So atomos, I think, perhaps specifies that there is this elemental um, particle which cannot be further broken down, right? So as soon as you see an electron can come out, can the atom can be ionized, uh, it suggests that atoms are not the most fundamental thing. There is substructure to atoms, right? Rutherford, using his experiments, we'll see in the next lecture or so, he gave an important uh, uh, idea on how an atom is, that a very small part of the atom holds on to all the positive charges. So a good analogy to remember is that if you imagine the atom to be a football stadium, a soccer stadium, the football is like the nucleus, right? Just this is a good analogy to remember. So most of the atom is sort of empty, and all the positive charge is in a very, very local region. Okay. So Rutherford's experiment gave rise to this understanding that we still retain on the structure of atom, wherein all the positive charge is localized in the nucleus, which is a very, very small part of the atom. Madame Curie got her second Nobel Prize in 1911 because the experimental techniques she used to isolate radium and polonium was these experimental techniques or separation techniques are more to do with the practice of chemistry. Chemistry and chemical engineering deal with separations and reactions. So Madame Curie got the second Nobel Prize for this work. Soddy was a co-worker with Rutherford. He contributed to a lot of early work on to good work on nuclear physics. So it was a surprise that he missed Nobel Prize in the early 1900s, but in time he continued to work, did very important work, and for the work on isotopes and radioactivity, Frederick Soddy got the Nobel Prize in 1921. There again another Nobel Prize in 1922 for Hahn for understanding and work in fission. He got in 1944, and Seaborg is probably one of the most famous nuclear chemists. There's a book also written by Seaborg on nuclear chemistry. He also developed a lot of methods that were, again, important in identifying important elements. He also contributed to some of the research, which is a follow-up of research started by Fermi. Okay, there's an element called seaborgium also. So he was important in unraveling trans-uranic elements. So as you can see, it's been a long time that the last Nobel Prize in chemistry, in nuclear chemistry, was in 1951. So it's been 70 years, uh, more than 70 years since there's been a nuclear Nobel Prize in nuclear chemistry, which suggests that new kinds of experiments have to be done uh, to get greater insight into nuclear chemistry. So with that, we move on to a next brief topic, which will be elaborated much more elaborately, but it'll be introduced briefly in the next lecture, which is on radioactive kinetics and artificial elements. Thank you.